So sometimes, right, our chemical equations are word equations. So what do you notice about the word equation? Rather than seeing your chemical symbols or your chemical formulas, you just have the words or the names of the substances written out. But that's not the usual situation for a reaction. Okay, and we're going to talk about the difference between the word equation and the skeleton equations. All right, so some symbols that we might see. Okay, so the plus sign could be used on either side of the arrow to separate our reactants and separate our products. So if you see that plus sign, that means you have two different chemicals on either side of the reaction. Okay, so the arrow separates reactants from products. Something you might not have seen before, the double-headed arrow. So double-headed arrow means the reaction is reversible. So as the reaction is proceeding from reactants to products, right, it could also be proceeding from products to reactants, kind of back in the opposite direction. So I'm sure you have seen these symbols before, right? S, L, and G. So the S, L, and G would be in parentheses, and it would kind of be placed right after the formula. That would indicate whether that substance was in the solid, liquid, or gaseous form. So that's just telling you what state of matter each of your reactants and products are in. Okay, something that might be new to you is AQ. Have you seen that before? AQ. So AQ means aqueous. So that stands for the word aqueous. And that means you have an aqueous solution with that substance dissolved in water. Okay, that's different than a liquid. A liquid means you have that pure substance, right, and it exists in a liquid form. Aqueous means you have taken that substance and dissolved it in water to make a solution. Okay, any questions about those so far? All right, and then a couple more things. Sometimes you will see something written above the arrow in your chemical reactions. Okay, so if you see this little triangle or the word heat written above the arrow, that means heat is required for that reaction to happen. Okay, so that means we add heat. Some things just won't react if you don't heat them up. And then if you see a chemical symbol, so this is just an example, it doesn't always have to be platinum, right? If you see a chemical symbol written above the arrow, that means that substance is being used as a catalyst. Platinum just happens to be a pretty commonly used catalyst. Okay, so if you drive a gas-powered car, that car would have something called a catalytic converter. Catalytic converter is made out of platinum. It's a very, very valuable metal. I don't know if anyone has any platinum jewelry, but it costs a lot of money. So there are people that actually go around and steal the catalytic converters off of cars. high dollar enterprise. Don't get any ideas, Natalie. She's like, I've been wanting some money to spend at Lululemon. Okay, so any questions about any of these symbols? No? Okay.
Wait, can you explain the aqueous solution again?
Okay, so aqueous, right? When you hear that AQU, you usually think like aqua, water, right? Aqueous just means, so if you saw something like this, okay, that means we have copper chloride dissolved in water. Okay, so it's a solution.
Oh, okay. Okay.
Yeah. So that copper chloride in its regular form is solid. Right? But a lot of our solids, especially ionic solids, in order to get them to react, they have to kind of be dissolved in water and broken up into their ions. It's different than something like H2O, where you would see the L next to it, right? Which means that pure water at room temperature is going to be a liquid. Okay, so this isn't necessarily pure copper chloride. This is copper chloride that has been dissolved in water to make a solution. So it's technically a homogeneous mixture of that substance and water. Okie dokes. All right, so now we're going to talk about the difference between a skeleton equation and a balanced equation. Okay, so a skeleton equation is an equation that doesn't have the same amount of atoms of each element on both sides. So skeleton is not yet balanced. Okay, and the way to tell is to count your atoms of each element on both sides. Okay, so here's our reactants, here's our products, and on both sides of that arrow we should have some copper and some hydrogen. Copper, hydrogen. Okay, but let's count how many of each we have on both sides. Okay, so how many, that's not copper, silly me, carbon. How many carbons do we have on this side? One, right? If you don't see a subscript there, it's understood that there's just one. How many hydrogens? Two. Okay. Over here, how many carbons? One. Hydrogen? Four. Okay. Do we have the same number of atoms of both elements on both sides? Okay, so this is a skeleton equation. Right? Because the atoms of each element, bless you, are not equal on both sides.
So does that mean it's just not a real equation?
It's a real equation, it just hasn't been balanced yet.
Okay.
Okay, so skeleton equation, right, just means not yet balanced. Okay, so a balanced equation uses coefficients most of the time. Sometimes you'll have an equation that's balanced without any coefficients. To balance the atoms of each element on both sides of the arrow. Okay, so think about what a coefficient means in math class. Right, if you had this expression, right, bless you. Which number would be your coefficient?
2.
The 2, right? So the number that comes before or in front of that expression is your coefficient. The numbers that come before your chemical formulas are coefficients. Okay, so that's a coefficient. Okay, and then what are these numbers called? Subscripts. Good. Okay, what does the subscript tell me? So if I have H2, what does that 2 tell me?
There's 2 hydrogens.
2 hydrogens, and they are,
Gases.
hmm?
Gas.
They're gases, but those 2 hydrogen atoms,
They're bonded.
they're bonded, right? So the subscripts tell me how many atoms of each element are bonded together, right? Right? So the subscript says, all right, I have 2 hydrogens, 2 hydrogen atoms, but they're held together by a bond. Okay. Now the coefficient tells me right, that I have 2 of those molecules taking part in the reaction. Okay, so the coefficients don't imply anything about being bonded together. They're just saying I have 2 of those particles taking part in the reaction. So H2, when you see the subscript, means, all right, those are the things that are bonded in one molecule. The coefficient says how many molecules are taking part in the reaction. Okay, do you feel like you understand the difference between subscript, coefficients? Okay? All right, so the reason that we balance equations is the law of conservation of mass. You guys have all heard this law before, right? Matter can neither be created nor destroyed, it can only be rearranged. Don't worry, I'm going to come back down, right? This equation here, before we balance it, implies that we started with 2 hydrogens and somehow 2 more hydrogens just appeared out of nowhere. That doesn't happen, right? So the law of conservation of mass as far as chemical reaction goes means atoms have to be conserved on both sides of the reaction. So if I start with 2 atoms of hydrogen, right? Those 2 atoms of hydrogen have to be there on the product side. They're just going to be rearranged into something new. Okay? So mass and atoms are always conserved in a chemical reaction. Okay? Highlight that, star that. Make sure in your notes you make note that that's an important thing to know, okay? Okay, so let's take a look. Let's look at this particle diagram here. Right? The red ones are our oxygens. Okay, so that's 1, 2, 3, 4 atoms of oxygen. So that means I should have 4 atoms of oxygen on the other side of the equation too. They're just going to be kind of mixed up with into new substances. So I have 2 oxygens here and 2 oxygens here. So I still have my 4 atoms, right? But they're just now kind of mixed in different compounds. So here I have 4 hydrogens. Do I see 4 hydrogens on the other side?
No.
1, 2, 3, 4. Okay. 1 carbon. Do you see it on the other side? Right. Okay, so that's what we're doing when we're balancing our equations, is we're accounting for the fact that atoms aren't kind of appearing out of nowhere or disappearing into thin air. Whatever is there before these things react have to be there after. Okay? Okie dokies. So some rules for balancing, or not rules, steps. And the good news is these first 2 steps are most likely going to be given to you, the correct formulas of reactants and products, and then the skeleton equation. That's most likely going to be given to you, and then you have to balance. So really 3, 4, and 5 are what we're going to focus on. All right, so step 3, right? The first thing that you do is you count the number of atoms of each element on both sides of the equation. All right, the only thing that we change or add when we balance is coefficients. Never change the subscripts. Because what happens if you change the subscript? You change the number of molecules being bonded, which means you change the substance, which means you don't have the same reaction anymore, right? So we only change coefficients, never change subscripts. Oh, you know what? It's time to go to lunch. No. I'm wrong. Sorry. That was a mean tease. Genevieve got really excited. 12:40. I guess we. Well, I'll let you go at 12:35 because I think the lunch starts at 12:40. Okay? Don't let me forget, Gianna. All right. And then once you get that equation balanced, then you want to make sure your coefficients are in the lowest possible whole number ratio. And I'll show you an example of what that means. Okay? So now we'll just go through a few examples and see how you feel. We'll start with a really easy one. Not this one. This one's not easy. Well, that one's not too bad. Easy peasy. All right, so on both sides we have hydrogen and oxygen. Ho, ho, ho. Okay. How many hydrogens?
2.
2. How many oxygens?
2.
Okay. How many hydrogens on this side?
2.
Oxygens?
1.
1. Now you want to say, okay, what element is out of balance?
Oxygen.
Oxygen, right? I don't have enough oxygens on this side. So what coefficient can I put here to balance my oxygen?
2.
2, right? So let's start with that. Okay, so now I have 2 times 2 hydrogen, which is 4. 2 times 1 oxygen, 2. Alright. So sometimes when you add a coefficient, it's now going to throw one of the other elements off balance. But can I look on the other side now and figure out where I can put a coefficient to balance my hydrogen? What would you do, Kylie?
Put the 2 before the hydrogen.
Right, if I put a 2 here, right, am I balanced now?
Yes.
Yes. Okay. Very common question, right? Is the 1 necessary? No. But some of my students just really like to fill in all the blanks, so it's okay if you put the 1 there. But the 1 in chemistry, coefficient, subscript, is not necessary. 1s are understood in chemistry. Okay. So, the lowest whole number ratio thing that I told you. If you had gotten 4, 2, 4, right? Because the coefficients that we use in balancing are a ratio, okay? So those coefficients would get it balanced. But now you want to look at those coefficients and say, all right, is there a greatest common factor that they can all be reduced by? Right? So each of those could be reduced by 2. Okay? Does that make sense? That's what that lowest whole number ratio, that step 5 of the balancing means. All right, let's look at another example. Okay, so what I want you to understand about balancing, we're starting simpler. they will get more complicated. And this is hard for honor students sometimes, but sometimes you will have to use your eraser and try something new, right? That's okay. Even I have to do that. I've had equations that I've tried to balance in recent years where I stared at them for like 15 minutes. Doesn't mean you're bad at it. It just sometimes it takes a little trial and error, and one thing doesn't work, so you want to try a new thing. Okay? So that means we're going to have to get a little gritty. Students hate when I talk about being gritty, like the Flyers guy. Okay, so let's count up our atoms. We have aluminum, oxygen, aluminum, oxygen. Okay? How many ALs on this side? Oxygens?
Two.
ALs?
Two.
Oxygens?
Three.
3. So here's something tricky, right? The first thing I would notice about this one is 2 oxygens on this side and 3 on this side. So whenever I see that, the first thing that I would want to do is I would want to get my oxygens to an even number on this side first, right? Because whatever you do on this side, that oxygen is going to stay an even number, right? So what could we try here to make our oxygens even? 2. Okay, that gives me how many ALs?
4.
How many oxygens?
6.
Good. Right, now what would we do? Kylie?
We put 4 AL and then 3 O2.
Right, 4 AL and then put a 3 there. We good now? Are they in the lowest whole number ratio?
Yes.
There's no greatest common factor, right? Alright, let me give you, I don't see you tomorrow, right?
No.
No, I'm gonna give you 2 to do for homework. Terrible. Okay, so once you get those written down, you can pack up, head to lunch. Oops.
Wait, is that a 4 missing?
Is what?
Is that 4?
Oh, P4?
Yeah.
Yeah, the students don't like my 4s for some reason. I don't know. I guess I write them funny. P4O10. Okie dokes? Alright, have a good day. Yes.
Did you get my email that I'm not gonna be here?
I
for
did,
Monday
yes.
and
So what you wanna do is you wanna follow along with the, assignment doc and link up with a student, that can send you the notes. I'm gonna try to remember, like I did today, to record